We'll look at some more word problems or application problems here with some other directional measurements and probably a bit more detailed versions of the previous ones. So the term bearing is used in navigation designated direction. The bearing is expressed only in degrees, is measured from a north line and in a north line in a clockwise direction. So you can see that illustrated here in a couple of quick examples. This is a bearing of 123 degrees, so here's our imaginary north line. We go in a clockwise direction until we get around to here. So bearings are typically used in aviation or in navigation with ships and airplanes. So if our plane is flying on a bearing of 120 degrees, it's flying along this line. Same thing up here, we have a bearing of 29 degrees. So here's our north line once again. Our bearing is measured in a clockwise direction. We go down 29 degrees. And again, if our ship is sailing on a bearing of 29 degrees, it's out here. Now bearing or heading might be interchangeable terms there. Bearings can also be expressed using measured from either a north or a south line, and then an east or west direction. This we typically use if somebody were using a compass or something like that. So we have two examples here: north 35 degrees west, or south 50 degrees east. The bottom line is you have either a north or a south line to begin with. You have an acute angle in here, and then you follow that up with what direction you're going from, north or south, and that would be east or west. So here's our north line. We're going north 35 degrees to the west, so this would be our bearing or our heading right along this line right here. And then south on our paper goes down 50 degrees to the east, that goes to the right, and this line right here would represent our south 50 degrees east. So you'll see those two types of directional measurements in our types of problems here as well, in addition to our angles of elevation, angle of depression that we talked about the other day. So let's take a look at what that looks like here. Radar stations A and B are on an east-west line 3.7 kilometers apart. Station A detects a plane at C on a bearing of 61 degrees. Station B simultaneously detects the same plane on a bearing of 331 degrees. Find the distance from A to C. So as we mentioned the other day, my personal opinion is you read through the entire question, which we just did. Now go back through it piece by piece and put our diagram together. So stations A and B are on an east-west line. East-west, right to left on our sheet of paper. They are 3.7 kilometers apart, and we'll just probably put those in order A and B. So we're here and here. Station A detects a plane at C on a bearing of 61 degrees. So our bearing is measured from a north line in a clockwise direction. So we're going to go around this way until we get to 61 degrees, or just estimate 61 degrees. So I'm going to put my plane out here at C. Actually, I'm just going to leave that blank for now. Since I've already worked this problem before, I have an idea where it's going to be, but this will help us out. So this angle right here, once again, is 61 degrees. Next statement, station B simultaneously detects the same plane on a bearing of 331 degrees. So from here, we go north, and if I go around to 331 degrees, that would put me right around in here. So my bearing here is 331 degrees. Again, bearing measured in a clockwise direction. So I'm going to get rid of this line that I don't need, and you can see where they intersect. That's where our plane is at, so we'll call that point C. And it wants us to find the distance from A to C, or this distance right here. Okay, so a couple things to note here. If we look at this first angle, angle A, I have an east-west line and a north-south line, so they are perpendicular, which means we have a right angle here, which means that this is 61, then this is 29 degrees, 90 minus 61. Same thing applies over here. I have a north-south line right here. If I go all the way around, let's do it this way. If I go from here to my east-west line, that's 270. So 331 minus 270 gets me 61 degrees, which means this angle up here is 180 minus 61 plus 29, or it is a right angle. And now that I have a right angle, I can apply one of my 6 trig functions, or one of my 3 trig functions. So let's say I look at the 61-degree angle. I'm going to use sine, because in relationship to the sine of that angle, the 61 degrees angle, x is my opposite side, and 3.7 is my hypotenuse. And if I take 3.7 times the sine of 61, we get angle, or side x, to be about 3.24, or if we go to the same decimal place, about 3.2 miles away. Okay, so there's a look at our bearings. Let's go ahead and try that again. A ship leaves a port and sails on a bearing of north 47 degrees east for 3.5 hours, then turns and sails on a bearing of south 43 degrees east for 4 hours. If the ship's rate of speed is 22 knots, which is nautical miles per hour, find the distance the ship is from port. I'm going to scroll down so we've got some more room to work with. Just here, randomly, I'm going to put my port out in the middle of the page. Ship leaves port and sails on a bearing of north 47 degrees east. So from here, we're going north, and we go 47 degrees to the east of that. Let's estimate that to be somewhere in here, 47 degrees. I'll come back to the 3.5 hours here in just a little bit. From there, it turns and sails on a bearing of south 43 degrees east. So from here, I'm going to go south, imaginary south line, and 43 degrees east of that would put us out in here. We're going to go for 4 miles and find the distance the ship is from port. So we're going to find the distance from the port out to our ship out here. Now I go back here. My first ship was traveling for 3.5 hours at 22 knots, which is 3.5 times 22, or it went 77 miles. My second ship traveled for 4 hours at the same rate of speed, so it went 88 nautical miles, or just say 88 miles. So we have 2 of our sides. We want to find our third side. I can't use the Pythagorean theorem, at least just yet, because I don't have a right angle. So that's going to be my goal here, is to find a right angle. So we take a long, hard look here. I have a north-south line here and a north-south line here. They are parallel. They're cut by this transversal. So if this is 47, alternate interior angles tell me this is also 47, and 47 and 43 make that a right angle. So here is our right angle. And now that I have a right angle, x is my hypotenuse, so 77 squared plus 88 squared will equal x squared. And if I plug that in, we get side x, or our distance from port, be 116.93 miles, or we'll say 117 miles from port. Okay, so there's a look at 2 problems that show our different measures of bearing. One just as a bearing, and one as north and east, or south and east, whatever the case might be. Let's continue on here. Francisco needs to know the height of a tree. From a given point on the ground, he finds that the angle of elevation at the top of the tree is 36.7 degrees. Moves back 50 feet from the second point. The angle of elevation at the top of the tree is 22.2 degrees. Find the height of the tree to the nearest foot. In this case, we already have a drawing drawn for us. So here is our tree, obviously, with our height labeled. Francisco started here. His angle elevation, horizontal line up to our line of sight, was 36.7. He backed up 50 feet. Angle elevation was 22.2 degrees to the top of the tree. So we've also labeled this unknown side right here as x. So what's going to happen here is we look, we do have a right angle here. The height of our tree is a vertical height and a horizontal line. But I have 2 different right triangles here. I'll take this one to begin with. I have that triangle. If I look at that, I have the tangent of 36.7 equals h over x. I have 2 variables. I can't solve one equation with 2 variables. So I go back and look again. I have an outside triangle right here that's also a right triangle. I could say the tangent there of 22.2 degrees equals h, but my base looks like it's x plus 50. So both of those equations have 2 variables. Unfortunately, by themselves, I can't solve that, but if I work with those together, I can solve that. So I'm going to take and use my calculator to find the tangent of 36.7 degrees, which is about 0.7454. I'm going to multiply both sides by x, so I have 0.7454x equals h. I'm going to repeat the process here with our tangent of 22.2. Find the tangent of 22.2, which is about 0.4081. Now, to get h by itself, I'm going to multiply both sides by x plus 50. So over here I have x plus 50, or 0.4081x, 0.401 times x, and that times 50 is our other value, and that's about 20.4. So plus 20.4 equals h. Now, if you'll notice, I have two equations that are both set equal to h. 0.7454x is equal to h, and 0.4081x plus 20.4 is equal to h. So I can say those two equations, 0.7454x, are equal to each other and solve for x. Okay, so in this case, I'm going to subtract 0.4081x to this side, so I combine my like terms. So that will give me the x, a 3, a 7, a 3, and a 3 is 0.3373 equals 20.4. I'll divide both sides by 20.4 divided by that 0.3373, and that gets me h to be about, or x, sorry, 60.49 is how far I'll go. How? We've gone through a lot of steps, but we haven't solved for h just yet. Remember, we want to solve for h, not for x. We're trying to find the height of the tree. I'm going to take this value, the 60.49, and plug it back in for x in one of my two original equations, so either here or here. This one appears to be easier to work with, 0.7454 times 60.49, and that will give us the height of our tree. And that height is about 45, I'll put the decimal on here, 0.09, so our tree is about 45 feet tall. Okay, so we had an equation there with two variables, two equations to go ahead and solve through. We'll go ahead and start over again. Surveyor on a mountain road 524 feet above a lake was asked to calculate the distance across the lake. Surveyor measured the angle of depression of the near and far edges of the lake to be 66 and 26 or 27 degrees respectively. Determine the distance across the lake. So we'll start here with our first statement. The surveyor is on a mountain road 524 feet above a lake. Above indicates a height, so we're 524 feet above the lake. Surveyor up here. The surveyor measures the angle of depression of the near and far edges of the lake. So angle of depression from our surveyor is measured from a horizontal line. So we'll go to the near edge of the lake, and we'll say that that is 66 degrees. Then we'll make our lake right here. The angle of depression to the far edge of the lake is 27 degrees. We want to find the distance across the lake. So the first thing we need to do is make sure we have a right angle here. So I'm going to extend this line over and make my right angle here. Vertical height with a horizontal line, so I have a right angle. Because I have a horizontal line here and here, I have parallel lines cut by two different transversals. If this is 27, then this is 27. If this is 66, then this is 66. So I'm going to re-sketch the large outside right triangle. So here I have 524 feet. I have a right angle, and I have a 27 degree angle. I'm just going to label the entire base as a single variable. I'm going to call it z. Okay, so from here I could say the tangent of 27 degrees equals 524 over z. Shortcut version, z equals 524 divided by the tangent of 27. So z is going to equal about 1,028.5 feet. Okay, so this entire distance all the way across the bottom is z, or 1,028 feet. Now, I'm also going to copy this smaller right triangle where I have a 66-degree angle, or just re-sketch it, I should say, not copy it. 66 degrees, right angle, 524. So I'm going to call this distance y. I'm going to do the same thing. Tangent of 66 degrees equals 524 over y, or y equals 524 over the tangent of 66 degrees. And y is going to equal about 233.3 feet. So we found the entire distance across is 1,028, and the shorter distance is 233.3, which means the distance across the lake is simply the difference of those two numbers. So if I subtract 1,028.5 minus 233.3, 259, looks like 795 feet across that lake. Okay, so not two variables, but we did have to use two triangles. We could have done it with two variables, but I think going one variable at a time in this case made a lot more sense. Let's go again. To determine the height of a mountain, the surveyor measured the angle elevation at the top of the mountain from 2 points 500 feet apart. The two angles of elevation were 35 and 40 degrees. To the nearest 10 feet, how high is the mountain? Let's start with that. How high is the mountain? Height of something, vertical height. Our angles of elevation by our survey were 35 and 40 degrees. So over here, we'll just put 2 points where he measured the height of the mountain. One to here and one to here. Now those angles are always measured from a horizontal line. So each of these is a horizontal line. Those 2 points were 500 feet apart. This then is a closer angle, so it's larger, it's 35 or 40, and this angle is smaller, so it's 35. If I continue on, first thing I want is a right angle, so I'm going to extend this out and have my right triangle here. I don't know the length of this dotted line, but it does part of that right triangle, so I'm going to put that as an X. And I'm going to do the same thing I did up above. I'm going to sketch those two triangles. So this will be the triangle around the outside, all the way around the outside. That means I have a 35-degree angle here, H here, and this little part is 500, the rest of it is X, so my actual distance across the bottom is 500 plus X. So over here to the side, I'll write the tangent of 35 equals H over 500 plus X. I'm running out of space there, so I'm going to slide over here to the side and recreate the other right triangle that I have here. So I'll sketch it real quick. That gives me a 40-degree angle here. This side is labeled as X and this side is H along with our right angle. So here the tangent of 40 equals H over X. So you can see same situation comes that we had a few problems ago where I have two equations with two variables. I'll start with the tangent of 40. That's about 0.8391. So this equation right here, 0.8391. Let's try that again and not transpose that. So 0.8391. Multiply both sides by x, so I have h by itself. 0.8391 x equals h. This equation over here, I'll find the tangent of 35, which is about 0.7002, so I'll mark that up here. We multiply both sides by 500 plus x, so if I take 0.7002 times 500, I get 350.1. Take it times x, I get 0.002x, and now I have that equal to h as well. Notice both equations are set equal to h, so I'm going to set them equal to each other. 0.8391x equals 350.1 plus 0.7002x. I'm going to solve for x. I want to subtract the 0.7002x from both sides. And that gives me 0.1389x equal to 350.1. If I divide by 0.1389. That will give me x, and in this case x is about 2,520.55 feet. And as we've already seen, we don't want to solve for x, we want to solve for h. We're trying to find the height of our mountain. So I'm going to bring this value back to this equation. So h is going to equal 0.8391 times that value, and times 0.8391, and I get 2,100, oops, let's try it over here, 2,114.9897. Oh, we'll go with 2,115 feet. It did say the nearest feet, so in this case the actual nearest 10 feet would be 2,110. I think in this case we would take either one of these answers and be fine with that. Okay, so there's another look at our two variable question. Let's try again here. Like we have two more to zip through here, I hope anyway. Veronica and Jose are located 1 mile apart on the ground. They observe a blimp directly above the road connecting them. Jose measures the angle of elevation of the blimp to be 53 degrees. Veronica measures the angle of elevation of the blimp to be 22 degrees. Find the height of the blimp above the ground. First statement, Veronica and Jose, 1 mile apart on the ground. Second statement, a blimp above the line, the road connecting them, says directly above, so it's just directly above the line. Because the angles are different, the blimp is actually closer to Jose because his angle is larger, so I'm going to put the blimp closer here and say our angle of elevation, or the angle from our horizontal line looking up, is 53 degrees, and the angle elevation for Veronica is smaller. It is only 22 degrees. But we do want to find the height of the blimp, so this line, height, coming straight down. Now, because those two angles are different, that means our altitude does not cut the base of this triangle in half. In other words, let's kind of slide down here. I have a right triangle on this side with Veronica, a 22-degree angle, trying to find h, and a right angle, but I don't know the length of this side, so I'm just going to call it x. I have another right triangle on the other side where I have h, a right angle, and 53 degrees. Since the entire distance across the bottom was 1 mile, and we called this x, this one will be 1 mile minus x. And we have another situation where we have our two triangles with our two variables. So I'm going to set up my two trig functions. Tangent of 22 equals h over x, and the tangent of 53 equals h over 1 minus x. The tangent of 22 is about 0.4040, so 0.4040x is equal to h, and the tangent of 53 is about 1.327, so it has to be multiplied by both 1 and x, so 1.327 minus 1.327x is equal to h. We have two equations that are both equal to h, so they're equal to each other, so let's put that down here. 0.4040x equals 1.327 minus 1.327x. We want to combine our like terms, so we'll add 1.327x to both sides. And over here we have 1.731x equals 1.327. We'll divide by 1.731. And x is equal to 0.7666. Again, make sure we solve the equation or the problem. We want to find the height. So I'm going to bring that 0.66 or 766 back up to one of my equations, all the way back up to here. Plug that in. H equals 0.4040 times 0.7666, and that gives us a height of about 0.3. I'm going to write it over here. Hope you can follow me here. Our height of our blimp is 0.3097 miles. What might happen here is we might make more sense of this by putting it in feet. So if I converted miles to feet, I'd multiply by 5,280. I'll go ahead and write that on here. Multiply by 5,280. So I can have my answer in either miles or as 1,635 feet above the ground. Again, either one of those is acceptable since it didn't say a particular distance up there in the problem itself. Oh, one more time. This might get to be a little bit redundant, but I want to go through these bearings one more time. Empire State Building is observed directly south of tourist A. A second tourist is 15 miles due west of tourist A and finds the bearing to the Empire State Building to be south 35 degrees east. How far is the Empire State Building from tourist B? First statement, Empire State Building is observed directly south of tourist A. So I'll put A right here, and we'll go straight south to the Empire State Building. Next statement, a second tourist is 15 miles due west of tourist A. So straight west would go out this way, 15 miles. So stopping right there, due south, due west, there's a right angle. This tourist is tourist B. He measures the angle to the Empire State Building, or the bearing to the Empire State Building, to be south 35.7 degrees to the east. So common mistake, people want to throw this angle inside the triangle. That's not how it's read. It's read and written as south 35.7 degrees east. This angle right here is our angle. And we want to find how far the Empire State Building is from tourist B. So there is our function. Couple of choices here. We have a north-south line here, a north-south line here. So this is 35.7, this is 35.7. Or we had an east-west line here, a north-south. So this is a right angle. 90 minus 35.7 will make this angle 53.3 degrees. How about 54.3 degrees? 54.3 degrees. So either one. In this case, I'll use the 35.7. That would tell me to use the sine. The sine of 35.7 equals the opposite side, which is 15, over the hypotenuse, which is x. I'm going to flip-flop those two, so x equals 15 divided by the sine of 35.7 degrees, and 15 divided by the sine of 35.7 is going to get us our answer, 15 divided by the sine of 35.7. X equals about 25.7 miles away. Okay, so there's some application problems using our trig functions.